All right, ladies and gentlemen, let's nail it dead on this one. This one, we're going to talk about the fundamental theorem of calculus. We've talked about that, but let's slow it down, and I want to talk about some properties of integration that make integrating a lot easier. And I'm going to do it with some examples. I'm going to do it in an analytical, but not a real deep kind of way. All right, so let's take a look. Here's one. So here are two things, and I'm going to break it down to you via common sense, and it's going to make great sense on why this sometimes is helpful. Sometimes calculating the area, and this is kind of the whole point, when we do the area of this and we do the fundamental theorem of calculus, this turns out to be f of b minus f of a, right? Well, this one would clearly be f of a minus f of b. And then we would need to make it negative to flip it around so it does actually match the fundamental theorem of calculus. So those two are equivalent. So what's the moral of the story? Sometimes you might be confronted where you have one number that's ahead of another number. And it doesn't really come because normally the interval is from 2 to 3, but for some reason, just how the notation works out, we're saying so for example, the integral from say 2 to 3 of a function, I'm not going to tell you which function it is, that area, maybe I will do it. No, I won't. It would be the same as the same thing, except you're going from 3 to 2. So we're talking about just in terms of like the actual math part of working it out. You'd have to take the opposite of it to actually get the exact same answer for these two to be equivalent. Okay, so that's what we're trying to say here. That interval from 2 to 3 is very, 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 very crucial. All right, in the order of what it is. So you want to make sure naturally it goes from least to greatest. Otherwise, you wouldn't really need the first property. But it does occur sometimes just during the calculations. All right, let's look at property 2. Property 2 is kind of the fun one. Okay, and this one kind of makes the most sense on an interval a to b. So I'm going to draw this one with picture. So let's got a guy on the right. Here's an interval a to an interval b. And I'll make it even bigger. I'll make it even bigger. I'll make it even bigger. Here's your interval a to your interval b. Okay, and let's say the function looks like this beautiful blob. Okay, so when we find the guy on the right, this is the area from here to here that we're finding. Okay, now what they're telling you here is that if you have some number in between there, c, right, some c in between a and b, okay, and let's say you were to break it up, and instead you found the area from a to c, right? And then you found the area from C to B, that number in between the B, that would be the same as finding the area from A to B. Now this is very, very useful because that means that you can now split up split up integrals if you find a number to split it at, right? And you can just choose any arbitrary number, but it could split up. And you can also join them together. So why do extra work and do two integrals when you can just do one? That's a huge deal. So that's the whole point. That is all about if you split the interval up, then that's the same as if you did the entire interval together. Makes good sense. All right, moving along. All right, check out this one. The integral from from a to b of f of x gives the area above minus the area below. Okay, on the x-axis. Now, what the heck does that mean? Well, let me draw you a bigger, in-depth picture. Okay, a to b of f of x. We've been telling you that this thing, dx, we've been telling you that this is equal to f of b minus f of a. Now, but hold on a second here. Do you guys remember what f of b was? F of b was the integral from a to some number t of f of t dt. And then this guy, which is f of a over here, well, that's the same as saying the integral from a t to a of f of t dt. Now this is probably meaning nothing to you, but it's going to mean something to my picture I'm getting ready to draw. And this is using the fundamental theorem of calculus. That's all I've done. It just looks really weird. So this says that we're actually going to end up having, this gives me the area up to b, and this one is going to take away the area up to, say, a number a, which I'll make that number a here. So it takes away this area. That's what we're doing here. And that is going to give us just this golden area, which is the area from A to B. So the way to think about it is that one comes in and gives you the area from negative infinity all the way to a number, done. And then the other one comes in, and because it's a little less than, it takes that stuff away, and then what you're left with is the area from A to B. So that's what they're trying to say to you in this picture. Yeah, looks really filthy, but bottom line is this is just another way of writing what you already know in the fundamental theorem of calculus. Done. So it's a little bit more technical, though, than what it leads on to. All right, now this is a cool one, and we've already learned about this. And what does this mean? That if I were to add all the heights of the areas together and then sum them all up from A to B, well, that would be the same thing as if I were to sum them up individually. That's all that's saying. No big deal here, okay? And I think I'll prove this with something we would have already done. Let's say at x squared plus 3x dx. Time to go back to basic understanding of things. We normally would do this. Well, this ends up being x cubed over 3 plus 3x squared divided by 2, and we would evaluate this from 1 to 2. And then we'd plug numbers in and subtract and da-da-da-da-da. Right, we'll keep going with it. Versus doing the integral from 1 to 2 of x squared plus the integral from 1 to 2 of 3x, well, this is still going to be x cubed over 3 integrated from 1 to 2. No c, this is a defined integral. This is 3x squared divided by 2 from 1 to 2. So if you notice, we're still going to plug in to get an answer here and get an answer here, right? And then add it all together. So it's effectively going to be the same thing. So that's why it's okay to split up the integral if you choose to. And you'll often find that this is often helpful when the integral is a very large thing you're integrating. All right, moving on. Number five. Well, whatever you can do, this was probably more intuitive. Whatever you do with subtraction, well, if it's negative area, you'll be subtracting it off. I don't think I really have to explain this one too much. This one makes more sense than anything. All right, if you knew the last one. Now, this one, property 6, is probably the most interesting because it basically says if you have a constant, you can factor it out. Okay, so why does that make sense? Well, because of rates of change. So, for example, I say, let's say we're going from 0 to 1 of the function 2x. Well, and let's compare that to 0 to 1, but I want to double the function of x. Okay? Well, are they the same thing? In fact, if you integrate this, this will be 2x from 0 to 1, which gives you 1 minus 0, which is just 1. That's easy, right? And then, but I still need to multiply it. I don't need to multiply by 2 because the 2's already been taken into account. Well, if I integrate this one, I end up getting x squared divided by 2 from 0 to 1. And then that means that that'll be 1/2 minus 0. But isn't that still effectively 1? Okay, so what's the moral of the story? And you'll notice this with almost every mathematician you meet. If they have a constant in there, they always pull it out because they don't want to look at the thing that's not changing. You just got to make sure that when it comes out of there that you multiply it by everything. That's the biggest place. All right, very simple, guys. The next video, we will finally use all these good things to actually anti-derive and get some real answers in the next application and examples video of anti-differentiation. I'll see you guys in the next video.